Hi, this is Mrs. Villette. In this video, we're going to talk about the substitution rule and how it relates in particular to trigonometric functions. The first example we're going to try is the integral of tangent of t dt by substitution. Now, when I look at this, I'm a little confused why substitution is the technique that's suggested, because I only see one function. And usually when we use the substitution rule, we're trying to look for a piece of a function or an inside u, and we're trying to find its derivative existing somewhere else in the integrand. And I don't see that in this case. So notice I mentioned that this is a single function, and we usually want two functions. Well, one way that we could deal with this is actually to change this tangent into two functions. We know a fundamental trig identity that tangent is the ratio of sine and cosine. So I can rewrite this as the integral of sine of t over cosine of t dt. Now you might be wondering what I should use as my u, because cosine and sine both have some sort of derivative relationship with each other. And in this case, I want to go with the cosine simply because it's in the denominator, and its derivative, sine of t, is in the numerator. So I am going to let my u be cosine of t. Then my du is negative sine of t dt. And if I reorganize that, I can say negative du is sine of t dt. And I notice that right up here in my integral, I have a sine of t dt. So that is my negative du. And then right here, I have a cosine of t, and that is my u. So I can rewrite this as the integral of negative du over u, which I could further simplify as negative 1 times the integral of 1 over u du. Now I just need to find an antiderivative of 1 over u. That's a known function. The antiderivative is the natural log of the absolute value of u plus c. Now we need to go and we need to back substitute because our original expression was not a function of u, it was a function of t. So I'm going to back substitute my t value, and I have negative natural log absolute value of the cosine of t plus c. Okay, moving on with some other trig examples. We have tangent multiplied by secant squared. We're trying to find the antiderivative. This one is a pretty straightforward u substitution. If I let my u be tangent of t, then I can see that my du is secant squared t dt, and I can quite easily see secant squared dt is going to be replaced by du, and tangent of t is going to be replaced by u. So I've changed this to a much simpler integral. It's the integral of u du, which is of course u squared over 2 plus c, and then I replace the u back with tangent. Now it's always a good idea to check your work to see if it makes sense. Remember that when we are doing substitution, we are trying to reverse engineer the chain rule. So what I want to be doing is taking the derivative of this function with respect to t. I don't need to take the derivative of the constant because I know that's 0. Now notice I've rewritten this so the square is on the outside, and I know in order to take this derivative I need to do the chain rule first. So the derivative of the outside function is 2 times the inside to the first, and then I multiply that by the derivative of tangent, the derivative of the inside, which is secant squared. And then the 2's cancel, and I get my integrand as desired. So example 5 is a little bit different because it's a definite integral, so we have the bounds here. And it's also similar to the tangent problem, only a single function. But it's not really a single function because this is a cube. So the first thing I'm going to do is I'm going to try to split up that cosine cubed into something else. And I'm going to split it up into cosine squared x times cosine of x dx. So now at least I have a product of two functions. Usually we're looking for a function and its derivative, but cosine isn't its own derivative. Cosine is the derivative of sine. So maybe there's something that I could do to rework some piece of this to involve sine. And the thing that I have at my disposal is the Pythagorean identity. I can rewrite cosine squared as 1 minus sine squared x times cosine x dx. So just rewriting that cosine squared as 1 minus sine squared using a Pythagorean identity. Now the u on this is a little bit trickier. We're going to just let the u be sine of x, because then the du is cosine x dx. Now, when we have a definite integral, we need to change our bounds. So we need to evaluate the u at pi over 6. So that means I need to know the sine of pi over 6, which is a half. And then we also need to evaluate the u at pi over 2, which is the sine of pi over 2, which is 1. So here's how this integral changes over. My bounds have changed to 1/2 to 1. Those were evaluating my u, which was my substitution, at the endpoints from the definite integral. Sine was my u. So now I have 1 minus the square of that u. So 1 minus the square of u. And then the cosine of x dx, I can see that exactly matches with my du. So I have the integral of 1 minus u squared du, and it's a definite integral, so in the end I'm going to get a number out of this expression. So antiderivative is u subtract u cubed over 3, and we are evaluating that over the interval 1 to 1/2. So we just evaluate at 1, so 1 minus 1/3, minus, and then at a half minus an 1/8 over 3. Just do a little bit of simplifying in common denominators. So the first one is 2/3 subtract a half minus a 24th. I'm going to build everything up to 24ths. So 16 24ths subtract 12 24ths subtract 1 24th. That should say 24 there. So putting it all together and subtracting, we should get 5 24ths. Now if you wanted to check this, you could check this in Desmos just by entering in the original integral. Now of course Desmos is not going to give you the answer in a nice form like the exact fraction, but it does give you the decimal approximation, and I can see that the answer that I got, 5 24ths, has the same decimal expansion as the original problem. So there's some other tricks that are commonly used when we are dealing with trig integrals. One of them is the power reducing formula. So this is basically a version of the half angle identity that you had in trigonometry, and this is a way that you can break down sine squared into something that doesn't involve squares. So this is useful if you have, for example, just the integral of sine squared x dx. I would rewrite that as the integral, I'm going to actually distribute 1/2 minus cosine of 2x over 2 dx. Now each of those on their own are not too difficult to evaluate. This would be x over 2, and I have to do just a u substitution on the 2x to recognize that I'm going to get sine of 2x over 4 plus c. I typically do those u substitutions that just involve constants in my head and then just run through the derivative to make sure that it works. So if I do the derivative of sine, I'd get cosine of the same period, and then I would do the derivative of 2x, which is 2, that 2 over 4, which would reduce to 1/2, which matches my original function. So that's an example how you do the power reducing formula if you had just a sine squared or just a cosine squared. We just used this one, so the Pythagorean identity was used in this last example. And then there are also the Pythagorean identities or Pythagorean theorems that have to do with tangents and secants and cotangents and cosecants. Our last look at trigonometric integrals is going to relate to things that look like derivatives of inverse trig functions. So you should recall that the derivative of inverse sine or arc sine is 1 over the square root of 1 minus x squared. We're going to try to use that to evaluate the integral from 0 to 1 over the square root of 4 minus 3x squared dx. And you're probably thinking, how on earth am I going to do that? Well, what we're looking for here is structural similarities. The fact that the denominator has a square root and on the inside has a constant minus something where the variable part is squared. The most important thing, surprisingly, is actually going to be getting this 4 to a 1. So the way that we're going to get that 4 to a 1 is we are going to factor out a 4. The way that we factor out is just by dividing out. So in order to factor out a 4, I'm going to make this a 1. 4 divided by 4 is 1. And then I'm going to have 3 over 4x squared. So just double check if you distribute back through, you get your original thing. Now I can just do a little bit of algebra. I can bring that square root of 4 out of the root as a 2. And I'm going to do something a little tricky here. I'm going to try to write this second term as the square of something. Well, obviously there's an x in there, and then probably over 2. Then it's going to be the root of 3. So let's see if that makes sense. If I want to write something as the square of something, I just take the square root and then square it, and then I've got it back to where I wanted it to be. So square root of 3, if I square that, gives me 3. 2 squared gives me 4, and then x squared gives me x squared. And I forgot a very important part, which is the dx. So this is looking structurally very similar to this, with the difference being this term right here. In the original one, it's x. Here it's root 3x over 2. That's actually what our u is going to be. So we are going to let u be root 3x over 2. Then that means my du is root 3 over 2 dx. Now, unlike the previous examples, I don't have a root 3 over 2 sitting over here anywhere in my integrand. So what I'm going to do is just do a little bit of rearranging, some cross-multiplying, some proportion work, and I'm going to say that 2 over root 3 du is equal to dx. So when I go over here, this whole dx is going to be replaced with this whole thing right here. Okay, so a couple more things. Pull the 1/2 out. Now, one thing I need to do anytime there's a u substitution is change out my bounds. So I need to do u at 0. U of 0 is just 0. We're plugging 0 in right here. So my bottom bound is 0. And then u evaluated at 1 is the square root of 3 over 2. Okay, now we have changed everything over to u's. So the dx is 2 over root 3 du. So notice I've replaced the dx with 2 over root 3 times du. I still have this 1 here. And now I have the square root of 1 minus u squared. So how does that help us? Well, this expression right here looks exactly like the derivative of inverse sine of u. Since we're doing an antiderivative, then my answer is going to involve inverse sine of u. So constants are going to hang out here. We'll cancel in just a minute. Then we are going to say the antiderivative is inverse sine of u. I don't need a plus c. The reason I don't need a plus c is this is a definite integral, and since I changed everything over to u's, including the bounds, I do not need to change back to x. So when I do my evaluation part of the fundamental theorem of calculus, I am plugging in a value of u that's 0 and a value of u that is the square root of 3 over 2. So I got a little sloppy with my u substitution, so I'm going to just go up here to do the rest of my work. So I have 1 over the square root of 3, and then I have inverse sine of root 3 over 2 minus inverse sine of 0. So remember, this is inverse sine. Inverse sine is asking at what angle is the sine root 3 over 2. And of course, we're only looking at angles in the first and fourth quadrants, positive angles in the first quadrant, and that looks to me like pi over 3. So this is 1 over root 3 times pi over 3 minus the inverse sine of 0 is asking me at what angle is the sine 0. Well, that's right here at 0, so minus 0. So our final answer is pi over 3 root 3. You can rationalize that, you cannot rationalize it. I'm fine with you just leaving the answer like it is. So that is my final answer. And what that represents is that represents an area under this function from, not this function, sorry, this function, the integrand from 0 to 1. So I would encourage you to look at derivatives of other inverse trig functions to try to see how you could use the same technique. So for example, I could ask you to do the integral of 1 over 4 plus 3x squared dx, which is very similar, and the answer is going to be something involving arctangent. Because once I factor out a 4 and do the little trick with writing the second one as a square and do a u substitution, I'm going to get to something, some sort of constant, so there's probably going to be like a b over a 1 plus u squared du. So there's going to be some constants that come out from the u substitution and the factoring, but I'm ultimately going to end up with a 1 over u squared. So take a look at some examples like that, and next time we will focus on what to do with rational functions for substitution. In this last part of the video, I'm going to fill in the basic steps for how to find the antiderivative of both secant and cosecant is actually very similar. So looking at the answer that's given in the textbook, I can see it's a natural log of the absolute value of secant x plus tangent of x. So I know at some point I ended up with a 1 over u du, where the u was secant x plus tangent of x. That's the only way that I could have gotten an answer that looked like that. But the strange thing is, I don't see a secant x plus tan x anywhere in here. So I'm really just going to reverse engineer this answer, because this is not something that I would have thought of on my own, and it's not something I would expect you to think of on your own. I'm going to multiply the top and the bottom by secant x plus tan x. So I'm multiplying by a special version of a 1. And when I do this, that's going to get me what I want in my denominator. And it turns out to work out really nicely, so that my denominator is secant x plus tan x, and my numerator is secant squared x plus secant x tan x dx. Now if you look at this and you let your u be secant x plus tan x, then your du is secant x tan x plus secant squared x dx, which is exactly what I have up here in the numerator. So that is my du. And then right here is my u. And now you can see I have the integral of du over u, which is the natural log of the absolute value of u, where of course my u was secant x plus tangent of x. So again, this is kind of a weird little trick, and reverse engineering it is the only way that I would have known that that's what we need to do. It's a very similar approach with cosecant of x, but I believe that you're going to multiply by cosecant plus cotangent instead, and that will give you sort of a similar setup and lead you to the answer that's given in the notes.